Hello again, Mrs. Thompson here, and today we are talking about intermolecular forces. Okay, before we can start talking about intermolecular forces, I have to mention intramolecular forces. Now, intramolecular forces are the forces within the molecule itself. And so that hydrogen to chlorine bond right here is considered an intramolecular bond. Make sure you write this down. It's the bond within the molecule. It's happening between the two atoms themselves. These bonds are very strong. They're what hold the atoms together. Then you also have the intermolecular forces. Now those are what hold two different molecules together. Okay, so here I've got HCl and HCl. They are actually attracted to each other. It's a weak attraction. It's not as strong as the bond itself. It's a weak attraction. And it holds one molecule to another. So it's between molecules. Whereas intra was inside of the molecule or within the molecule. Alright, so we need to know about intermolecular forces because it helps us to figure out why solids, liquids, and gases behave the way they do. And so here it says intermolecular forces can make it difficult to pull molecules away from each other. Which means as they pull away from each other, they are changing state from solid, liquid to gas. And it is these intermolecular forces that keeps them held together tight. And so you see this picture here of these particles splitting away from other particles, breaking those intermolecular forces. Okay, here we have a chart of the three phases of matter. And it goes through the change from solid to liquid to gas and how the particles have to separate. Okay, and what you have to do that. So to get a solid to turn to a liquid, you melt it. And those particles move away from each other. Okay, so a couple things we need to know. In a solid, the particles are close together. In a gas, they're far apart. The reason for this is because of their intermolecular forces. Now, intermolecular forces in a solid are really strong, which keeps them close together since they're attracted to each other, whereas intermolecular forces in a gas are very weak, and therefore it doesn't hold them close together. It actually allows them to spread out. All right. When those intermolecular forces are strong, it says we need extra energy to get them to change state. And what this does, and this is what we're going to spend the next part of this chapter doing, is we have to know that those intermolecular forces raise the boiling point, makes it so you have to add more energy to get them to boil, raises the melting point as well, so from solid to liquid, and it lowers something called vapor pressure, and we'll get into that later. Okay, so we are going to go over 4 types of intermolecular forces that hold these molecules together. There are actually more than this, but we're only going to cover the intermolecular forces that hold particles in a liquid and in the gas form. There are some extra ones that hold particles in a solid that we're not going to cover. You can cover that in AP chemistry if you decide to move on. All right, so London dispersion forces are the first type of force that we need to know. So you know they are an attraction between temporary dipoles. Okay, dipole. What is a dipole? A dipole is something that has 2 poles, a positive end and a negative end. Okay, so what causes these temporary dipoles is a polarization of electron clouds. So an electron cloud gets shifted, ends up having more electrons on one side than the other. And so then you end up with a positive end and a negative end. So it's not normally polarized. It's normally nonpolar, but for some reason, the electrons just kind of shift for a second. That's why we call it temporary. So it ends up being polarized. Factors that will change the amount of London dispersion, so the strength of London dispersion forces, are an increase in molar mass. The reason an increase in molar mass changes the strength is because you'll have more electrons around that particular atom or molecule. So I want to draw your attention to the pictures down here, which have been flashing. So here's the first one in the corner. Here we've got two neon atoms, and they come close together, and what ends up happening, neon is normally not polar, what ends up happening is all the electrons get shifted to one side of the neon atom. And so the side where it shifts to becomes negative, the other side is positive. Well, if that happens in both of these, okay, and this just naturally happens, the electrons naturally get shifted. If that happens to both of them, then you end up with one that's positive, one that's negative, so they're going to attract like magnets. All right, there's another picture here of different molecules. Let's say this is hydrogen. So you've got the nucleus of hydrogen here, and then you see the electrons are moving. Well, if the electrons are on one side more than the other, that side becomes negative, and the other side becomes positive, and then that positive and negative attract each other. Now, molecules that can do this, associated molecules. Actually, everything has London dispersion forces. All atoms, all molecules. Specifically, things that tend to only have London dispersion forces are noble gases, diatomic elements, so hydrogen, H2. Remember Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, those aren't going away. Those all would have just London dispersion forces. And any other nonpolar molecule. So hopefully you remember about polarity and how to look at the structure of a molecule to determine whether it's polar or nonpolar. Okay, to show you how London dispersion forces are actually important, what you can see here is three different halogens, chlorine, bromine, and iodine. Chlorine, having a lower molar mass than bromine and iodine, has less London dispersion forces. So what you end up with is chlorine in the gaseous state. Liquid bromine, because it has a little more London dispersion forces, keeping those molecules together in the liquid form. And then iodine, having a greater molar mass, meaning it has lots of electrons that can get shifted, is in the solid phase. Okay, next force, dipole-dipole. And as it sounds, it's the attraction between two dipoles. And these are permanent dipoles, meaning that they are already polar. There's already a difference between the pole of electrons within that particular molecule itself, like hydrogen chloride. Hydrogen chloride has a permanent dipole, meaning it has a positive end and a negative end, because chlorine is more electronegative than hydrogen, and it hogs those electrons. And so the cause here is the positive and negative attraction of molecules that are already polar. Now, if you're comparing two polar molecules, and this is only if you have to do that, what you would do is to figure out which one has the strongest dipole-dipole forces is you would look at the difference in their electronegativity. So if I had HF versus HCl, well, fluorine is more electronegative than chlorine, and so HF would have a stronger dipole-dipole force than HCl. All right. Associated molecules, anything that's polar. So you might need to draw the Lewis structure, or if you have something easy like HCl, you can see that hydrogen and chlorine are pulling those electrons at different strengths, so it's already polar. All right. So here we see this little animation of a hydrogen and a fluorine, or chlorine. And so this positive end is attracted to this negative end. All right, next one, hydrogen bonding. Hydrogen bonding is actually dipole-dipole forces, but it's a really strong dipole-dipole. To memorize which dipoles can do this, it's anytime you have hydrogen bonded to either fluorine, oxygen, or nitrogen. So you would have an H to F bond, or an O to H bond, or N to H bond. And we say it's hydrogen bonded to fun, which sounds like fun, which intermolecular forces are fun. Come on. All right. The factors that increase it. Well, in terms of electronegativity, fluorine is the most electronegative. So therefore, fluorine with hydrogen would have a higher intermolecular force, stronger intermolecular force than oxygen to hydrogen or nitrogen to hydrogen. So that's if you're comparing different molecules. Or the number of hydrogen bonding sites. So if one molecule has 2 hydrogen bonds within that molecule versus one that just has 1, then the one with 2 is going to have a stronger intermolecular force. All right, and then the associated molecules are, these are the most common. Hydrogen to oxygen is water, nitrogen to hydrogen is ammonia, and then H to F, hydrogen fluoride. But you can also have other molecules that have that O to H bond. And we see this a lot with hydrocarbons, like alcohols. Okay. Or an amino acid with something with an NH2 group. All right, next one, ion-dipole. So this one you see less commonly in terms of when you're doing your homework. But an ion-dipole is just an attraction between an ion and a polar molecule. Okay, so if we throw in an ion in there and something that's already charged, something that already has a positive and negative end, then that ion gets attracted to that. All right, so it says ion attracts oppositely charged end of a polar molecule. So you see this animation here. What happens is I put sodium and chlorine in water, the sodium and the chlorine break apart, and then the water molecules are attracted to an ion of sodium and an ion of chlorine separately. And you'll notice the way that they're arranged around that ion is differently because those are different charges. So this sodium atom right here is positively charged, or ion, excuse me. These negative ends, which is the oxygen, because oxygen's more electronegative, are actually attracted to the sodium and they surround it. In this one, chlorine's negative, so the positive ends of water are attracted to the chlorine, which is the hydrogen in water. All right, factors that can increase this. So if you have to compare 2 different ion dipoles, okay, then you would look at the charge of the ion. So if I'm looking at, let's say, this one, sodium, which has a 1+ charge. We're actually looking at the magnitude of the charge. Versus if I had calcium, which is a 2+ charge. Okay, calcium having a greater charge would be stronger in terms of those ion dipole forces. Another thing that could change it is the polarity of the molecule. So here these are attracted to water. If I put them with something like HF, which has a stronger electronegativity, which means that that molecule is more polar, then that one will be the stronger one. All right, associated molecules. Really, I'm not going to give you too many of these, but mostly what you'll see is water with some ionic compound like sodium chloride. So it's usually in solutions of water and an ionic compound. It really does not have to be water. It could be any other molecule that's polar. All right. Okay, here's the table that you already have. Hopefully you have that all filled out. But what we need to know now is, in terms of strength, which are the strongest ones and which are the weakest ones? Well, here's the trend. The London dispersion forces are the weakest, and the ion-dipole are the strongest. Just make a note of that off to the side, or if you can't fit that in there, just write increasing strength right on that arrow that you have. All right, so let's figure out what we're going to do with these problems. Here we go. We have our first one, which is HCl. We have to figure out if it's polar or non-polar. To do that, I'm going to draw the Lewis structure, which could lead to drawing the Vesper shape. For this one, I really don't need to because it's obvious that it's linear. And so I need to look at electronegativity. Chlorine has a higher electronegativity. We can tell that by the trend. And so what ends up happening is it holds on to the electrons better, making it slightly negative. Hydrogen is slightly positive. Since there is a difference here, this is polar. It has 2 poles, a positive end and a negative end. All right. What does that mean for its intermolecular forces? So we're going to go down the list in that chart to see which ones it has. All right. So first one is London dispersion. Since all molecules have London dispersion forces, this has London dispersion forces. All right, next one is dipole-dipole. In order for this to have dipole-dipole forces, it has to be polar. And look, this is polar, so it has dipole-dipole forces. All right, next one, hydrogen bonding. In order to have hydrogen bonding, it needs to have hydrogen, which it has, but that hydrogen has to be connected to fluorine, oxygen, or nitrogen. So this has no FON, so it does not have hydrogen bonding. So it's just London and dipole-dipole. All right, CH4. This one I did have to draw to figure out that it is tetrahedral in shape. And since it's tetrahedral in shape and all of the outside atoms are the same, it is a symmetrical molecule, which means that it is nonpolar. Okay, symmetrical molecules are nonpolar. Remember, the poles cancel. Okay, so since this is nonpolar, let's go through the steps. Does it have London dispersion? Well, everything does. So this one does have London dispersion. Does it have dipole-dipole? No, this is nonpolar. So nonpolar molecules do not have dipole-dipole. So that one's done. All right, HF. Drawing the Lewis structure again. Looks just like HCl, except for it has an F. Fluorine is more electronegative than hydrogen, so it has most of the electrons most of the time, so it's slightly negative. Hydrogen is slightly positive, which means this is polar. All right, let's go through the list. Does it have London dispersion? We sometimes just write LDF. I didn't. I wrote London dispersion. If you want, write LDF from now on. All right, so it's got London dispersion forces because everything does. Does it have dipole-dipole? Well, it's polar, so it has dipole-dipole. Does it have hydrogen bonding? Well, it has hydrogen. Does it have FON? Yes, it has F. So it has hydrogen bonding. The hydrogen's attached to the fluorine. All right. Does it have ion-dipole? I noticed I didn't go over ion-dipole for all of them. As soon as you kind of stop down the list, then you're done. But none of these have ion-dipole. In order for them to have ion-dipole forces, they would have to have their molecule, like HF, plus another ion, like sodium. Okay, so no ion-dipole forces here. Okay, so we're going to pick between two molecules or atoms or whatever we have here to see which one of these has stronger intermolecular forces. All right, so here's the first one, neon and krypton. What do we know about neon and krypton? Well, they are both noble gases. Okay, noble gases. So let's see. These are just atoms, right? Noble gases. Well, all atoms, like noble gases, have London dispersion forces, and that's all they have because they're not polar. They're just atoms, so they just have London dispersion. So how do we tell which one has stronger London dispersion? Well, that's by which one has the highest molar mass, because it has more electrons. So between neon and krypton, krypton has a higher molar mass, therefore more electrons that can be instantaneously pushed to one side. So krypton would have stronger intermolecular forces. All right, oxygen or nitrogen. What are these? Well, these are diatomic molecules. Okay, and diatomic molecules also have London dispersion forces. They are both the same in terms of electronegativity between oxygen to oxygen, so they aren't polar. All right, so between the two, oxygen and nitrogen, we can look again at their molar mass. Well, oxygen has a higher molar mass, therefore it has more electrons that can get shifted, and therefore oxygen has stronger intermolecular forces. Okay, H2S or H2O. If I draw these out, they have similar structures. They both have a bent shape, and so bent is not symmetrical, and therefore both of these are polar molecules. All right, so both are polar. Okay. Both, therefore, since they are both polar, have London dispersion and dipole-dipole forces. London dispersion because everything does, dipole-dipole because they're both polar. Okay, but water can do something special. Water can hydrogen bond because it has hydrogen and oxygen. And so therefore, since water has hydrogen bonding, water has a stronger intermolecular force. All right. We are going to work on this, and please ask questions when you get to class.